So today's warm-up question says, which has more total current if the batteries and bulbs are identical? So we have two different circuits here. The one on the left is a series circuit. The one on the right is a parallel circuit, and it says that everything here is identical. So they have the same light bulbs, they have the same batteries. It's the only difference between the two is the way in which they are connected, series versus parallel. And so which one would have more total current? What do we think? Which one has more current, series or parallel? Parallel. Yeah, good. Parallel is going to have more current because it has less resistance. Okay. Again, whenever you're looking at the equivalent resistance for your series circuit, you're adding these together. Whereas when you do that with a parallel circuit, you are adding them, but as 1 over whatever that resistance is, plus 1 over whatever that resistance is. You've added another pathway, and so this will have less resistance and therefore more current. Okay, so more current in parallel because it has less total equivalent resistance. How does the current change if a third bulb is added to each? So a third bulb is added in series to the one on the left-hand side. If a third bulb was added in parallel to the one on the right, maybe it looks something like this now. Okay, so how would my current change? Looking at the series circuit, if I did this, is my current going to be more or less than it was before? Less. Okay, because I have just increased the resistance of that circuit. What about my parallel circuit? Will my current be more or less? More. Okay, again, when I add that other bulb, I'm not just adding a bulb, I'm adding a third pathway. That decreases the resistance even further, and that therefore will increase the current. Okay, so again, you need to remember those rules in how we analyze and interpret these different types of circuits. So again, please make sure you have answered this warm-up question in My Open Math if you haven't already done so. Okay. I told you we went over this question yesterday with some different numbers, but again, the reason I keep asking you this is because I'm telling you, you will see it again. But it says, if each resistor is a bulb, which would be the brightest? And this is another circuit that, kind of like the warm-up, has 3 bulbs that have exactly the same resistance, 5, 5, and 5. Okay, and again, if I want to determine which would be brightest, I need to analyze this circuit in terms of the power output at each of those resistors, at each of those light bulbs, because the one with the greatest power will be the brightest. Okay, and so we can analyze that in terms of just looking at the circuit and thinking about which one would have the most voltage, which one would have the most current, and not necessarily doing any math, or of course we could calculate the powers. But we're going to go ahead and do it kind of like we did yesterday. The greatest current is through R3. Okay, because these are all the same resistance, this is a little easier. This is my total current here. Each of these has half of it. Half of it goes here through R1, half of it goes through R2. It's going to split directly in half because those two have the exact same resistance. Okay, and so I know that this one has the greatest current. In fact, it has twice as much current as either of the other two resistors. Okay, I also know that my greatest voltage drop will occur where I have the most resistance. Obviously, each of these resistors has the same actual resistance rating for the bulb. However, when we're analyzing it, we need to look at the total resistance of the parallel section. Okay, because that's what's going to determine the voltage drop in that section. So again, we would solve it like this. 1 over 5 plus 1 over 5 is 2 over 5. Again, if that's equal to 1 over RT. I'm doing RT for just the parallel section, so I labeled it like that. So that makes the resistance 5 over 2, which is 2.5 ohms, which again, I already knew because these are all the same resistance. I know that the equivalent resistance of that parallel section will be half as much because there are 2 of them. Okay, so I can just divide it by 2. If they were all different numbers, of course, you would have to go through this process. But my equivalent resistance for this section is 2.5 ohms versus 5 ohms here. And so again, I will have the greatest voltage drop where I have more resistance, and that is this point right here, because again, I'm looking at this whole section. Okay, so even though the bulbs all had the same resistance, this one has more resistance than this section does. Even if it hadn't, even if they were all equal, it still had more current. But the point being, and we talked about this yesterday, you don't necessarily have to approach it with math, and it's almost always the bulb that is in series with the battery. Okay, if you have a combination circuit like this bulb that's out here not in the parallel section is usually the brightest one. But you can always go through and ask yourself these same questions, or you can go and you can do the math. Okay, so let's go ahead and look at how we would solve this problem. So I've already filled in the resistances 5, 5, and 5. I've already filled in the battery's voltage of 9 volts. So let's see what we can go ahead and solve for. We already solved for the equivalent resistance of this section, finding it to be 2.5 ohms, and we can use that to determine the total equivalent resistance for that whole circuit. Because if this section has a resistance of 2.5 ohms, I can now add that to this resistance because they're in series with one another. Okay, and so if I want to find the total, I'm going to take that 5 ohms from R3, that 2.5 ohms from that parallel section, and I'm going to get a total equivalent resistance of 7.5 ohms for the entire circuit. Okay, again, this is the same process we went through yesterday. Now that I have my total resistance for the whole circuit, I can start to look at what my total current would be because I know the total voltage. It's the battery. It's 9 volts. Okay, and so let's go ahead and solve for this total current value. Okay, again, voltage equals current times resistance. My voltage is 9. My total resistance is 7.5. So 9 equals I times 7.5. Divide both sides by 7.5, and 9 divided by 7.5 is 1.2 amps. And so that would be the total current in my circuit. Okay, and so we can fill that value in. I also know that that is the same current that goes through R3 because the total current has to flow through here. There's not another pathway. Now the total current does not flow through R1 and R2. It only flows here where you have both the red and the blue. So again, if you color code the loops, if you draw that circuit on your own paper, because you know the test is going to be a class set, you can draw it on your own paper. You can trace those pathways and then you can see this. So I've got these things filled in. The next thing that we can look at, and again, you can solve this in other order, but if I want to go ahead and solve for the parallel section, I can solve for the section as a whole. This is a different way than I did it yesterday, and this works too. So I'm going to show you more than one way. What we did yesterday was we found this voltage here, which we could obviously do right now, and then we subtracted it from 9 to get these, and you can do that. Okay, but you could also approach it like this. I can use the total current for the parallel section, the total current that flows into it, and the total resistance of that section to solve for the voltage drops in that section as well. So the whole current flows into it, that whole 1.2 amps. It does split, but the whole thing flows into it. And it has an equivalent resistance of 2.5 ohms, and so I can plug those numbers in to get the voltage drop for this section. And that's going to give me a voltage drop of 3 volts. So each branch in that section, they're going to be the same as each other, and they're both going to be 3 volts. I could have also, because these were all the same, I know that my current splits half and half, so I could have filled in the currents first in this particular case because I know it splits in half and had 0.6 and 0.6 and found my voltage that way. Okay, because 5 times 0.6 is also 3. So again, there's multiple ways that you can approach this. So I'm just showing you another way. Maybe you like this better. Maybe you like what we did yesterday better. It doesn't really matter. You're going to get the same answer either way. Okay, so now we can work backwards and find the current. I already know it's going to be 0.6 because these resistors are all equal to each other, and my current's going to split directly in half. But I can also now find it because I have V and R for resistor 1 and resistor 2, with the values are the same. And so I can go back to Ohm's law, and I can say 3 equals I times 5, which means I equals 3 over 5, which again is 0.6. We already knew that was going to be the case. But if we didn't have these nice pretty numbers, we would need to go through the process of doing this. Okay, and so my current flowing through each of those branches is 0.6 amps, and I can fill it in for both of them. I only put it here, but they are both 0.6. Okay, now if I want to find this voltage, again, it is right here on my third resistor. I do have a voltage drop, and I know that the voltage drops along each loop add up to the battery's voltage. So I could find it by subtraction, because let's say I'm looking at the red loop. I know that I have a voltage drop here on the red loop of 3 volts, and so I'm going to have another voltage drop here at this resistor, and they have to add up to 9. So I could find it by subtraction, or I could use Ohm's law again. V equals I times R, because I have both I and R for that third resistor. Again, there's more than one way to do this. Okay, so I'll go ahead and do it this way, but my voltage, if I'm looking, I'm doing it, actually I'm showing you both ways. So here we go, we have I times R, 1.2 times 5, or again by subtraction, because they have to add up to the battery's 9 volts, so 9 minus 3. Either way, you get 6 volts. Okay, so again, whichever way you prefer to go about doing this, but again, that voltage drop will be 6 volts. Okay, now that we have the rest of the table filled in, and again, I didn't type it in here, but this is also 0.6 amps. Now that we have the rest of the table filled in, we can use power equals voltage times current with the appropriate current and voltage drops to calculate the power through each resistor and to calculate the total power output of the whole circuit or the battery. But again, I didn't actually solve that, but you'd have 0.6 times 3, 0.6 times 3, 1.2 times 6, and then you could either add them all together or you could do 1.2 times 9. But if you were to do this, again, we could then show mathematically which one has the most power as well. Because we already said that we would have the most power through resistor 3, which you absolutely would. 1.2 times 6 is larger than 0.6 times 3. Okay, so you would get the largest power output here, and that is why this is the brightest bulb. So you can, again, prove it mathematically, or you can approach it more conceptually. Either way, you'll end up with the same answer to that question. Okay, I did also work through another combination circuit as a practice problem and record it yesterday. I think it was on slide 80. So if you wanted to see another problem worked out, I did, like I said, record that one yesterday after school, and I put it in the YouTube playlist. So you can go back and look at that if you want. One reason you might want to look at that video is if you would like to see how to use the calculator to solve the problem, because that's the one that had resistors of 10 and 8.7. And I said, this isn't really one where I would want to try to do this by hand with a common denominator. So I worked it out showing you how to use the calculator. So again, if you're not sure how to use the calculator in order to solve these problems, watch that video or try practicing it today and see if you can get it sorted out. But again, guys, you're going to want to make sure that you are comfortable with that, because you do have a test next week. You have a quiz on Monday, you have a test on Wednesday, and if you haven't been paying attention, you do not have school tomorrow. So this is our last day together prior to that quiz. Of course, we'll go over the quiz before the test. But again, I'm going to strongly encourage you to make sure that when you leave today, you feel as comfortable as possible with all of these things, including using the calculator to solve them, in the event that the numbers aren't pretty with a nice common denominator. Okay. Also, you are strongly encouraged, all caps, strongly encouraged to read slides 94 through 108. That's actually the following slide. I'm going to just click to it real quick past this equation one, if it works. It has a bunch of just basically a summary of the entire unit. And it goes through and it talks about and compares series, parallel, and combination with regards to current, with regards to resistance, with regards to voltage, brightness. It goes through some of those math equations as well. So I'm going to go back. But Again, that starts on slide 94, and I would just click through it between now and your quiz on Monday. Again, it's a good thing for you to read. If you do finish this assignment, today's assignment is 1104.4 mixed circuit problem set. It is due by 11:59 p.m. But if you do finish it early, I'm going to encourage you to work on the unit summary because that has extra practice for you, and that would be due by 7 a.m. before you take your test on Wednesday. Okay, go ahead and get to work. If you have questions, please make sure that you ask before you leave today, and please don't forget that you are going to be taking a quiz when you come back from your long weekend on Monday.